Good morning. So sorry for the delay. Few announcements before I start the lecture. So first of all, as you might have definitely known, we have published the feedbacks for Lab 3. We will start the demos on Friday for a week. So I'll send an email today, hopefully with more instructions. The process is going to be the same as lab 2. So yeah, wait for that email to get out. The second announcement is about the quiz. Quiz is, posted, and the deadline is today. Let me see. Yeah, so the third announcement is about the lectures. Including this one, we have 4 lectures. Unfortunately, I'm behind the schedule that I had in mind. So there are 4 topics that I want to cover going forward. What I'm going to do is from this lecture towards the end of the lectures, I'll start a new topic every lecture, and if whatever I cover, and whatever I can't cover, I'll post a video from last year so that you can actually watch the rest of it. Whatever I cover comes in the quizzes. Whatever I don't cover, you won't be asked about in the quizzes. So the basically the purpose is to cover as much as possible so that you get out of this course knowing those topics. But unfortunately, I won't be having time to go deep into each one of them. Okay, so with all of that, if there are no questions, I guess I'm going to start the lectures. So I'm going to actually now finish the caches as quickly as possible, and then I'll start the next one, which is paging. Okay, so I guess we were here. Yeah, we talked about access and dirty bits. So yeah, now there are 2 situations that we have to cover when it comes to caching addresses. The first one is homonyms. So what are they? So these are single virtual addresses that are single virtual address that is mapped to different physical addresses. How can that happen? Well, if you have 2 processes, each one of them has valid virtual address from 0 to the max, let's say 2 to 32 minus 1 or 2 to 64 minus 1. So you could have, I mean, in the range, you have all the virtual addresses are available to both processes. Now, each one of them could map it to a different physical address. Now, this is fine if you don't have any caches. If you have no TLB, for each one of these translations, you're going to go to page table entry, and each one of these processes has its own page table, so everything is fine. Now, if you put a cache there, then if you cache process 1's translation of its virtual address to physical address and you keep it in your TLB, and then you context switch, and now process 2 comes, when it accesses the same virtual address, you might think that you have that translation in your TLB, whereas it's an old translation. So one way you can do this, you can solve this, is to always, every time you context switch, you just invalidate all the TLB entries. That's simple, but it's expensive. For expensiveness, it's the main reason for it to be expensive is that you might actually context switch back to the first process. And now the first process has to again fill up the TLB from scratch. So a better solution is to add tag to every address translation in TLB, very similar to the tag that we used for general purpose caches. Now we can actually tag our TLBs with the process context identifier, which is basically the PID. So for each translation, we just tag it so that we remember which process this translation belongs to, so that the next process that comes with the same virtual address, although that virtual address is translated in TLB, we check the PCID and we say, okay, this is a wrong translation. The other issue that could arise in multiprocessors is making all the TLBs consistent with each other. So let's say that you have 3 processors, processor 1, processor 2, and processor 3, and they're all running your processes. And in this example, I have 2 process 1 and process 0 and process 1, and these two processes have been running on all 3 of these processors. So they have populated the TLB of these 3 processors. Now, let's assume that at some point in time, the code that is running on processor 1 decides to change the page table entry of process 0. Now, you can do that. Changing page table is sort of easy. It resides in memory. You can just go and change it. And potentially, we talked about keeping the TLB consistent with page table. That also is possible. So you can either invalidate your TLB or you can just not touch it, depending on the change that you made. But now what happens to the other instances of this cached translation, right? So in particular, look at this page 53 in hexadecimal. So this page exists in processor 1's TLB and in processor 2's TLB. Now, whatever I talked so far can manage this one. You can either invalidate it, or depending on the change that you made, you do stuff. But what about this one? So in order to get that done, you need inter-process interrupts. So processor 1 has to send a message to process 2 and process 3 because it doesn't know if they have cached this translation or not. So it will send them a message and tells them to invalidate that translation. And it has to actually wait for them to acknowledge that they have indeed invalidated that particular translation. So this process is called shootdown, and you have to wait for all the processors to acknowledge. As a result, the cost of this basically goes up linearly as you increase the number of cores that you have in your system. So this is one more challenging point that we have to deal with as a result of the hardware in multiprocessors. So now what happens if you don't find your translation in page table entry in your TLB? Well, you have to go and bring it from page table, right? Now, if you have implemented page tables in hardware, then a hardware, I think we call it page table walker. So a page table walker, a hardware page table walker has to just go through all the pages, all the page table entries and find that translation and bring it. If it finds a valid translation, it just found it, it brings it to TLB and the execution continues. However, if either you find invalid translation or the access is not correct, then hardware will raise an exception, and it tells the walker says to the CPU that page table was not what I expected. Now page fault. Now on a page fault, kernel decides what to do, as I've explained multiple times so far. Depending on the situation, you make a decision on what should happen. Now, if you have implemented page tables in software, then on every TLB miss, CPU is going to raise an exception. So you can see the difference. In here, after a TLB miss, you still continue. The hardware still walks through the page tables, but here the hardware doesn't have any idea about page table, so it has to raise a TLB fault. And then at that point, kernel wakes up and makes a decision on what to do. Now, this raises a question of how do we really handle exceptions? I never talked about that. I probably alluded to it in a couple of lectures ago, the concept of precise exceptions. Now, unlike interrupts, exceptions are synchronous. So interrupts, you're running a code and then your timer goes off. So it's asynchronous to your code. Whereas exceptions are synchronous, meaning that they actually are the results of executing a particular instruction. Maybe you divided by 0 and that raised exception, or maybe you accessed a file, an address that you were not supposed to, and that raised an exception. So they're synchronous. Now, in general, the instruction that caused the exception, we need to rerun it, right? If we take care of that exception. So if it is divided by 0, well, that we can't do anything. The software probably should terminate. But if for example, an instruction caused page fault, we were not supposed to, we weren't able to finish that instruction, and we have to redo that instruction. Now, here comes the tricky part. What happens if the instructions that we're executing have side effects? What do I mean by that? Here I have a bunch of examples. Let's say you have push 10. So you're going to push number 10 to your stack. And this instruction by itself, right, it has 2 steps. One is the stack pointer should increase, and then wherever it's pointing, you load your store number 10. So basically 2 parts. Now, what if when you increase the stack pointer, now it's pointing to some area that it's not supposed to, or it's not yet allocated, and it raises exception. So should you now, next time you run this push 10, would it again increase the stack pointer, or should it go back where it was? The stack pointer should go back. So that's one example. There is a side effect. And if we want to rerun the instruction, we have to take care of that side effect. Another example that is a result of out-of-order execution, which I talk a little bit about later on. So look at this example. So you have a multiplication. It's going to multiply R2, R3, and I guess R1 and R2 and put it in R3. No, actually. So it's going to multiply R2 and R3 and then put it in R1. And then you have a branch instruction that conditions on R1. If R1 is equal to R4, then it, if they are not equal, branch not equal. If they're not equal, then you go to loop, If they are equal, you continue. Now, in modern hardware, you do execute instructions out of order. So there is a possibility that, okay, this multiplication is going to take time because it's multiplying 232 bits, and it could take time. So you look at the next instruction. Next instruction depends on it because it checks at R1, and R1 has to be set by multiplier. So you might look at the third instruction. It's a load instruction. So here you load whatever is in an address of R6 to R5. So, okay, now let's say you want to do out of order execution. So you're waiting for this multiplier. You cannot do this branch. You start doing this load. But let's say for whatever reason, this R6 is pointing to an area that is not allocated, and that raises an exception. Now, maybe it was the case that the result of this R1 was not equal to R4, and you had to branch to loop, so you never needed to execute this load. But then you, because of out of order execution, you executed load, and it raised exception. What should you do? Should you process that exception? Should you ignore that exception? What has to be done? The same example with this divide. It's very similar. So to answer all of those questions, computer architects have come up with the idea of precise exceptions. And the idea behind it is that, well, you can execute instructions out of order, right? That's fine. But you should do it temporarily, meaning that whatever change that they make, those out of order instructions, they have to be changed. Their changes have to be applied to temporal locations. You shouldn't indeed change the architectural state of your processor. So what is exactly the architectural state of your processor? Well, your registers, the memory, these are your architectural state. And you don't need to really change those when you're executing out of order. So you can actually write the result of, let's say, a load somewhere, keep it there. You can execute it, but you don't need to submit it. That's the idea. So I guess the one thing that I missed in the previous slide was the definition of retirement. So when you retire an instruction, it means that that instruction, all the things that it had to do are now reflected in the architectural state. Now, basically, this one means that you can execute instructions out of order, but then don't retire them. Keep them until it's their turn, and then you can retire them. Okay, so that's the general idea. If you have taken any computer architecture course, you go deep into what that exactly means. But then basically you have a pointer, if you wish, that shows you how many instructions have retired so far. So as you run your code, the pointer might be here, and you're actually running some of the instructions down below out of order. And this pointer shows that this instruction yet hasn't retired. So, but you're still running out of order. At some point, this instruction retires, so you change the pointer. And now maybe there are some instructions here that you have already executed. So this retirement fastly, fast forwards because they have been finished. So you can just apply their result to your architectural state and just change the pointer. So maybe this pointer waits a little bit somewhere and then jumps, and then waits somewhere and then jumps because of that out of order execution. So that's the idea. Now, when it comes to exceptions, if an instruction down below raises an exception, we're not supposed to run that exception. We keep that exception there. Now, if this pointer ever comes there to that instruction, then we process the exception. if let's say this pointer, because of the jump, goes somewhere else, we just ignore all the things that these instructions in the middle did. We just throw them away because they haven't changed any architectural state. We're fine. We just throw them away, and then we continue from where we are. So that's basically the idea. And whenever we come to that instruction that raises exception, we process the exception first, and then we rerun that instruction. So at the end of the day, the picture that you get is that you're running a user code. A faulty instruction happens. You go, you manage that exception. You come back, you rerun that instruction, and you continue. Is there anything else I wanted to say? So, okay, so the takeaway was basically, as I mentioned, was this pointer that points to the instructions that have already retired. And because of having this pointer, even though you're doing out of order execution, it looks like you're doing in order instruction because this pointer goes with the same order as your program. Okay. So going back to the big picture, we put TLBs, right? Because address translation was absolutely too slow because of all those accesses. So we put TLB to improve the performance by caching these translations. How can we improve the performance even further? Well, have multiple levels of TLB. The same way that we had multiple levels of cache to speed it up, you can actually have multiple levels of page tables. So if you miss in page table level 1, you can go to page table level 2 and check it there. So in x86, for instance, you have 2 to 4 level page table walks. So as we saw, 2 in 32-bit system, 4 in 64-bit system, that's super expensive. So maybe add 2 levels of TLB as well. So that's an idea. The other way that you can actually improve performance is by introducing virtually addressed caches. So the idea of having a virtual cache, I guess the true name is virtually addressed cache, but you can see it as virtual cache as well. So what is the idea of this virtual cache? So the idea of virtual cache is instead of going to TLB and page tables to translate your virtual address to physical address, to then go to memory, you could actually cache the data that, so at the end of the day, your instructions are interested in data. So if I'm loading an address, I'm not interested in that address. I'm interested in the data in that address. So this TLB caches the address translation, virtual to physical address translation. Now this virtually addressed cache can do that by just caching the data corresponding to this virtual address. So basically this cache uses virtual address to cache data. So when a virtual address is issued, you check your virtual cache. If it is a hit, then you have the data, you come back very fast, super fast. And if you miss here, then you start doing the rest of it. So you translate your virtual address to physical address and do the rest. But if you hit here, well, you just found your data by your virtual address. Now this is cool, but it's not that rosy things. The first problem that could or should come to your mind is hononyms. What if now you context switch, you go to another process, has the same virtual address, and you check your virtual cache and you see that it's there. So what should you do? So in order to take care of those situations, you also have to add the PCDI or whatever that was, the process ID of each virtual address to your virtual cache. So that should be a no-brainer because of what I just explained. But that's not where it ends. There are other problems that you have to take care of, and the main one is synonyms. So what are the synonyms? So synonyms now are different virtual addresses that are mapped to the same physical address. Now, this could happen in two different cases. One case is that, let's say you have two different processes and they share data. Let's say, you know, they share a shared library. Now they could use different virtual ranges for the same physical address. So that would be a synonym. But this one is a little bit easier to handle than the second case of synonyms, where within the same process, you could have different virtual addresses mapped to the same physical address. So this is absolutely possible and very hard to deal with. So one example for this, you can actually check it yourself, is if you use mmap, memory map. So if you use mmap twice in your program to map a file, the same file. So what is the idea of memory map? Memory map basically gets a file, maps it to memory. So it allocates a range of virtual memory to you, and it maps it to that file. So now from now on, whenever you want to write to that file, you can write to those virtual addresses. So basically file operations, you can do file operations by load and store. And that's beneficial because the alternative to that is to use the system calls to write to a file or read from a file. And we all by now know how expensive system calls are. Now, the downside of memory map is, what if, you know, your system crashes, all your changes are gone because all of your changes are in memory until you explicitly ask the operating system to write them down to the hard disk. Whereas with system calls, when you write, it actually writes to the hard drive when you do that. I mean, there are buffers, and then you probably have seen it in 254, where you have to use, you know, you have to explicitly tell the operating system there as well to make sure that all the writes that are buffered are written to the hard disk. But I mean, similar, but a little bit different as well. So now, if you run mmap for the same file twice or 3 times or 4 times in your program, what happens is that each time you run, it gives you a new range. So all of these new ranges that you get, all of them are mapped to the same physical memory. Now, why is that a problem? Well, it actually leads to aliasing problem when it comes to virtual caches. Now, if you cache, let's say in your virtual cache, if you cache both of these two addresses, and both of them are, you know, the data for both of them are the same. They're 2 different virtual addresses, but they're mapped to the same physical memory, so they should have the same data. Now, let's say you write to one of them. If you write to one of them, well, you can write in you go to your cache, you see that this virtual address, the data for this virtual address is this, so you change that. But then how does your cache know that there is another element in the cache that is mapped to the same location that you also have to write? Because if it doesn't, next time if you use the other address and go to your cache, you see the old dated data. You don't see the updated data because the updated data is now mapped to another virtual memory, and you're checking the other virtual memory, and now you have inconsistency between between your data. So how do we solve this? A typical solution for this is virtually indexed but physically tagged virtual caches. So what you do is you use virtual address, but then you also tag it with the physical address. And that means that you will, when you look at your virtual memory, you will see this physical tag twice in my previous example, because both of them have the same physical memory, so both of them get the same tag. So if you write to one of them, now cache has an idea that it has to go and check all the tags and write to all the elements with the same tag. So that's how you basically solve it. It's super expensive, like you have to, add a lot of tags and stuff. So, but it's worth it because how much it saves us from going to TLBs and page tables and files and memory. So it's doable. And the synonym problem will affect any hardware structure that uses virtual memory for indexing. So another example of these hardware instructions are store buffers. So for those of you who know about store buffers, they also use virtual memory to find data, and they will have the same problem that we just faced with virtual cache. So for those, you also have to use the same techniques to resolve the issue. Okay. Yeah, I'm going to actually move on from that one. Okay, so now here is just putting everything that we talked about in the previous lectures, all of it together. So this figure shows you a typical multi-level address translation. You have a page table pointer. You use the first few bits to index into it. That gives you a pointer to second level page table. You use the next few bits to index into this one. And then this gives you a physical page number. You use the offset to then find a specific byte in your physical page. So that's basically address translation 101. Now, what TLB does is basically TLB caches this virtual page number, both of them together become one virtual page number, two physical page number. So instead of going through all the TLBs, all the page table stuff, you can just come check your TLB. TLB has cached. If TLB has cached your virtual to physical translation, you are saving yourself the pain of going through your page table, and you're done. So this is TLB. Now, the other thing that you could do is to add actual caches. This is not a virtual cache. This is like, level 1 cache, level 2 cache. These are physically addressed caches because, as you can see, I'm using physical address. So you can actually cache your data. So instead of going to physical memory, you can actually go to your cache first and see if you can find your data. The way that works is that you get your physical address, you break it down to byte, index, and tag, and then you use those to find your data in your cache. And if you have it, then you just use it without going to physical memory. And this is basically putting it all together in one picture. So there is virtual cache, there is TLB, there is page table, and then I also have added the physical caches here. So if you don't find your data in your virtual cache and you have to go to TLB, then at this point, once you have the translation, before going to physical memory, you go to your physical cache. And if you find it, good, you have the data. If not, now you have to go to physical memory. In reality, you have multiple levels of this physical cache. So it's not just one, you have multiple levels. again, in reality, you might have multiple TLBs as well. So TLB level 1, TLB level 2, TLB level 3. The same with virtual cache. You could have virtual cache level 1, virtual cache level 2, and so on and so forth. Now, this is basically what we added then. So to add performance, to improve performance, we added this TLB. It sits where the registers sit inside the processor. It's super fast, but it's also very small, similar to TLBs, similar to registers. I think many systems have, max 256 entries in TLB or less. So it's very expensive, so you have only few elements in your TLB. Page table resides here, so if you miss in your TLB, you have to bring your page table. But things are not that bad because you can actually cache these page table entries in your level 1, level 2, level 3 caches. So it could well be that elements of this page table, as you read them, as the page table walker tries to access page table entries, it could also cache them in L3, L2, and L1. So if you miss in TLB, you might not need to go all the way to memory. You might actually just go to L1 and find it in L1. Or if you don't find it in L1, you might find it in L2 or L3 or your main memory. So caching the page table entries could also help us improve the performance. So you can actually put now one important aspect that we have to talk about is set associativity of TLB. Now TLB is a cache, and then caches have set associativity, if you remember. So if you look at this, you have the hit time plus miss ratio times miss time. Now, if you stare at this, you realize that you're paying this hit time for every single memory operation. So for every single memory operation in your systems, you're paying this hit time in TLB. So you have to go to TLB. Now, one might think that, okay, if I'm paying this in every single instruction, I better minimize this. Now, if you want to minimize hit time in your TLB, what should you do? Well, in terms of associativity. So if you remember, if you have direct mapped cache, it has the lowest hit time. And if you have fully associative cache, it's more flexible, but it takes more time to hit in cache, to find your data in cache. So maybe you can think of, okay, so I have to have a direct map cache. So so you might think that direct map is the way to go for TLB to minimize this. But one point to note is that if you use direct mapped cache for your TLB, then you're going to increase your miss ratio by a lot, because now every address is mapped to a single location in your TLB, and there is no flexibility, so there is a higher chance of missing in TLB. So then miss ratio goes up. If you remember, I told you that hit time and miss ratio move in different directions. So if you improve your hit time, then your miss ratio shoots up. If you decrease the miss ratio, your hit time is going to go up. So now in this case, if we were to choose between the two, if your miss ratio goes up, you're going to pay a heck lot of cost, because the miss time of TLB is enormous, is huge. Why? Because you have to now go and traverse your page table, and that's super bad, super heavily costed for the operating system to do. So if you were to choose, you should actually choose miss ratio. You should bring miss ratio down, and to do that, you basically need to have fully associativity. So if you make it fully associative, that improves your miss ratio. It degrades your hit time but this is a bullet that you're willing to take because of the high cost of missed time in TLB. Okay, so I guess I'm gonna jump from this. I kind of alluded to this concept of super pages in the past. So the idea is if you have sequential addresses in your physical memory, so let's say there is a huge file and you have mapped this huge file to consecutive addresses in physical memory, that gives you an opportunity to use to use page table entries in higher levels to just address the entire page. Because as you remember, when I was walking you through the 64-bit x86 TLB, page tables, where you had 4 levels of page tables, we talked about that the fact that the last one was covering 2 megabytes, and then the second level was covering I think 1 gigabyte, and so on and so forth. So let's say if you have 1 gigabyte, all of it mapped to sequential physical addresses, then you can just use one element of your page table level 3 to map to the entire address, and that saves you because you don't need to go now to page table level 2 and then page table level 1. So you save 2 accesses to memory by just having a super page. Now this also now means that when you want to cache it in your TLB, you also have to tell TLB that this is a super page, right? So it's not just in your page table entry you indicate that this is a super page, you also do that in your TLB. So I'm going to actually move on from that topic. The next topic I have in my slides, so I'm just, at this point, I'm just, telling you a lot of different stuff about virtual memory. So this is another thing that is important, which is basically Linux virtual memory map. So this one is the, I have to say, this has changed from 2018 as a result of a series of serious bugs that were found in hardware. Operating system, specifically Linux, made changes in virtual memory layout. But prior to those attacks and those vulnerabilities in 2018, prior to that, this was how virtual memory looked like in Linux. So in a 32-bit system, from address 000 until C000, the operating system would allocate that to the user address space and then preserve C0000 to FFFFF for itself. So no program could use this range of address because operating system would reserve that for its own kernel stuff. Now, in a 64-bit system, you have a bigger address space. The operating system gives you from this address to this address user space, and then there was this empty space that nobody could use. So basically, empty space, nobody would use it. And then from this address to this address, again, the kernel stack, the kernel address space. Now you might think, what's the point of reserving a certain address for kernel and not letting the programs use that address range and just keep it for kernel? The reason for that was performance. So the idea was, let's say, this program, a program that is running, calls on a system call. And then, well, system call is the functions for that system call, all of them are in kernel space. So at that point, you're running kernel code. So you will be dealing with virtual addresses in kernel space. And you might actually cache those translations as well. What's the difference between translating user virtual to physical address and kernel virtual to physical address? You might actually cache those. But then let's say you context switch to another program, and that other program also calls the same system call. Now you want to use the translation that you made in the previous one for the kernel stuff. You want to use that translation for the second one as well. So to be able to do this, they both need to use the same virtual range for kernel. And that's basically the idea, why you preserve a certain virtual address range for kernel, so that whenever you do the translation, you can use it in future context switches. So as you context switch, the range for kernel doesn't change. So all of them have the same range for kernel, so that if you cache it, then you can actually use it in future translations. And this is just not system calls, yeah, right? Interrupts as well, kernel page tables as well. So everything about kernel. The thing is, when you're running your user code, a lot of times you have to go to kernel. And if we make it consistent across processes, the range of virtual addresses for kernel, that makes life easier for everyone, because now you can do things faster by caching them. Now, the problem with this that was exploited by attacks like Meltdown and Spectre was that actually having to do this opens the door for some vulnerabilities that were exploited actually with Meltdown and Spectre. Unfortunately, I don't have enough time to talk about Meltdown and Spectre. So to just briefly mention what is going on, let me look at the time. To just briefly mention, the main problem with Meltdown was the fact that the processor does out of order execution. That's basically the main thing. The cherry on top was that to enable out of order execution, the processor has to speculate sometimes. Very similar to the example I had, where you had a multiplier and then a branch not equal and then a load, right? So in order for the processor to ignore the first two and start running the third one out of order, the underlying assumption is that the processor assumes that that branch not equal is not going to be taken, right? So it's probably safe for me to go and execute load, because if the branch is taken, then I have to go and execute whatever is in the loop, right? So because all of these branches, the hardware speculates that, okay, I'm not going to take this branch, or I am going to take this branch, so I can go and execute the instructions after that. Because if you have to wait for that branch, then your performance will be limited, because there are so many branches. And if you don't speculate about them, that basically means that you have to wait for that branch to have an answer so that you can go forward with your execution. Now, this is bad because you want to, be as fast as possible. You don't want to wait for that branch. You want to speculate and go forward. So two problems: out of order execution and then speculating on branches. That, I mean, generally speaking, without thinking about security issues, this was fine, because even if you mispredict a branch direction and you execute it out of order, it was fine. Worst case, you realize that it was a wrong speculation. You just throw away all the computation you did and then you start over. So, which is sort of fine. But this was shown to be a security vulnerability. And that was shown by Meltdown. So this was announced in 2018. It actually affected Intel processors, AMD processors, and some of the ARM processors. So again, I'm not going to go through this, or maybe I should. It's actually quite interesting. So the only thing that is important about it is that when you add caches to your system, caches are not architectural states. They are transparent to the programmer. Programmer doesn't do anything with caches. Caches are primarily used by hardware, but they actually leak information, caches. How do they leak information? Well, if you have cached a certain address and the program accesses that address, if you have cached it, the execution time of that instruction will be super fast because it's the data for that instruction is in the cache. If you haven't cached it, then you have to go to memory, and execution time of this instruction takes time. So if you have a smart programmer that can time the execution time of each instruction, then they can, just by seeing how fast that instruction was executed, they can infer that you have cached it or you haven't cached it, right? So that's the way for the programmer to know if the data is cached, by just seeing how fast that was executed. So this is basically a side channel leakage, because you didn't want programmer to know about caches altogether. You wanted caches to be, transparent. But now, by just looking at the execution time, programmer can infer information about things being cached or not. Now, how does this lead to a vulnerability? Well, let's say you have this array of 256 elements. You actually want to multiply it by this much so that you avoid prefetching, because you could prefetch, your hardware could prefetch. But if you have like 4 kilobytes between each element, so basically the first element is 0 times 496. The second element is going to be in an address of 496, basically 4 kilobytes between each element, so that if your hardware also does prefetching, it's not going to prefetch 4 kilobytes. So you're going to be fine between your 256 elements that you're interested in. So this becomes your array. You flush the cache. I'm not going to talk about how you do that, but assume that you could flush the cache. Make sure that your cache doesn't have anything. Then you do this try and catch. How can you catch? So the purpose of this try and catch is to catch a segmentation fault. You don't want segmentation fault to terminate your program. You want to catch it. So you can do that by programming the signals to catch the exception. Now, what do you do here? So in this one, you access a kernel address. So an address that you're not supposed to address. You try to address it, and then after that, the code after this is dummy equals array of the result, whatever you read. This is a byte multiplied by 496. Basically, you find the element in your array, and you put it in the cache in this dummy node, this dummy variable that you have defined. Okay, so let's look at this code. Now, this shouldn't, after this instruction, a segmentation fault should happen, right? Because you're addressing kernel memory, which you're not supposed to, and an exception happens, and things should be fine, right? You catch that exception and you continue. So in theory, this second instruction should not execute at all, because the first instruction is going to, lead to an exception. It's going to raise an exception. Now, because the hardware is greedy when it comes to performance and it wants to execute a lot of instructions, what it does, so one point before I go to the greediness of hardware, this single instruction could be divided into micro instructions. That's another important thing, right? Because look at this. This is just a load, right? You're loading the address in your memory to a register or to a variable. But in reality, you should be doing so many things. You should check for the access of this memory. You should read that memory. You should raise exception if the access is wrong, or if you don't find that translation in your page table. So this is not just one instruction. I mean, it is one instruction, but it is broken in a set of micro instructions that have to be executed. Bring the data, check the access control, raise exception if anything wrong happens, and so on and so forth. So there are so many different things for this single instruction that the hardware has to do. Now, hardware breaks it down to all these micro instructions, and then you have another instruction afterwards, which looks at this array and basically brings the data in this array and puts it in this variable. So that's another instruction. Now you have all these micro instructions. Hardware could do out of order. So it could first bring the data and then check for the access and then raise the exception and stuff, and then intervene the instructions afterwards in between them to just execute out of order and make it faster. So what happens is there is a chance that you do execute this instruction before the exception is raised. So it could well be that the micro instruction to read this address happens first, and then this happens, and then hardware checks for the access control and realizes that you don't have access, and then hardware executes another micro op to raise exception, right? But then at the time that exception is raised, you have already executed this instruction. Now it's fine with, if you remember, we had this idea of retired instructions and precise exceptions. So you don't retire this exception. You don't retire this instruction, and you raise exception for the first one. So everything is sort of fine. But what could happen in the background is when you access this array out of order, because you have flushed your cache, none of the elements of this array are in your cache. So if this instruction is executed out of order, your hardware, your cache now has this element. So it has come to the cache because the cache was empty and you accessed this. So the data for this has brought to the cache, but caches are transparent to programmers, so nothing is wrong. It's in the cache, so what? Well, here comes the code here to exploit that. As I said, you can time your instructions to see if a certain data is cached. Now, if I go through all the elements of my array from 0 to 256, that's all the possible values of a word, of a character, sorry. And then I time it, how long it takes to read this. The moment I find an I that I can read this fast, I know the value that was stored in this kernel address, because that's the element that was cached. And here here is the side channel, and here is the exploitation. I read the memory the data stored in kernel address space. And that's basically a vulnerability. Okay, so for Meltdown, after Meltdown, there were a bunch of patches to mitigate basically Meltdown, not get rid of it altogether, but to mitigate it, there were patches. One of the important ones was to basically not map the kernel address space to user address space. And that patch by itself could introduce almost 800 times overhead if your system didn't have the ability to invalidate individual TLB elements. So in old architectures where you didn't have any mechanism to invalidate individual elements and you had to get rid of all the TLB, then this patch could impact your performance by 800%. So it was pretty bad. But there is another attack called the Spectre, which affects even more. So in this one, I think AMD processors weren't affected, but the Spectre affects those as well. And the Spectre is actually worse in terms of it uses another technique, another side channel to read data from kernel, and for that there is no patch actually. So there is no real patch. There are mitigations, but they're not patches. And then hardware, the problem with hardware is, well, the hardware is shipped. So what are you going to do? There's no way for you to change hardware to have hardware patches. So that's pretty much where we are. Okay. So that's that. Let's start next lecture, which is about demand paging. I'm going to be as fast as possible. So I guess the conceptual idea behind demand paging is pretty easy now that you know about caches. So the main idea actually is, so the main idea is treating main memory, your physical memory, DRAM, as a cache for your permanent storage. That's the whole idea. So we use these L1, L2, L3 caches as cache for main memory. Now, what prevents us from using main memory as a cache for secondary storage systems? So that's the main idea. Now, why do we want to do that? Because virtual memory is huge, and if you are running bunch of processes, there is a chance that you cannot fit all of their data in your main memory. So if that's the case, then you have to pick and choose what data you want to have in your main memory, and the rest of the data that you choose not to have in your main memory, they're going to be stored in your permanent storage. So in a sense, you're using your main memory as a cache for your permanent storage. That's the idea. Yeah, so we call this caching, basically having the data in these caches. Now, having the data stored in secondary storage in main memory, we call it paging. So now, if you want to do that, then there are questions that you have to answer. What is the block size? When you're talking about main memory and physical memory, then your block size is basically page size. So the size of blocks in your memory, 1 page. What is the organization of the cache structure? Well, it's fully associative. You can put every page anywhere you want. So you have fully associative cache when it comes to main memory. How do you find your page in the particular page that you're interested in your cache. So you basically, all the things that we talked about so far, you look at your TLB. If you can't find it there, you look at your page table, and then that gives you a pointer to where your page is in your physical memory. What is page replacement policy? We're going to actually talk about this. So we're going to talk about a bunch of policies to pick a page to be evicted to make space for new pages to come. What happens on a miss? So if you go to physical memory, you don't find the page that you're interested in, what happens? Well, you have to go to secondary storage and bring it. So that's what's going to happen. What happens on the write? Well, you can actually do a write back, meaning that you don't need to write right away to your permanent storage. You just set a dirty bit. You wait for this page to be evicted. When the page gets evicted, then you write it to the secondary storage. So these are all the questions that you have to ask yourself every time you have a cache. Okay, so to do this, the bits in page table entry that are going to be of our interest are this valid bit. So this is basically how we make sure that we know which pages are now present in physical memory and which aren't. And then we use this access bit and dirty bit for our replacement policy. So, okay, so as I said, valid and invalid, we will use them. And then if you have a page that is invalid, you raise exception, you trap to OS, and then OS basically brings it, if it has to, goes to the secondary storage and brings that page that you're interested in. Now, to do that, the operating system has to allocate physical page to a new page that wants to come. Now, operating system looks at the physical memory. If there are space, if there are physical pages that are not allocated to anyone, then the question is easy. You just allocate those pages to the virtual page that you want to do the translation. But if there are no empty pages, then you have to pick a victim. You have to evict an already present virtual to physical cache, physical in your physical memory. You have to evict that physical page to make a space for the newcomer. And when you want to do that, you look at the dirty bit of that page that you want to evict. If it is dirty, excuse me, if it is dirty, you write it back to the secondary storage, and if it is not, you just throw it away, and you bring the new page. Once you realize, right, that you have to do eviction to make a space, you might not want to wait for this process to finish, because this is a expensive process to go to secondary storage and bring the physical page that you're interested in. So you might at that point context switch to another process and then do the demand paging in the background, so that you don't waste time waiting for the page to be brought back to memory. So yeah, this is the big picture. This happens if you have a valid page table entry. You just go to your page table, you find it in memory, everything is fine. But what if you go to page table entry and it's invalid? Then you raise page table exception. So now page fault handler wakes up. It goes to the disk, finds that physical memory in the disk, brings it to memory, updates the page table. It now makes it valid and makes it point to this. Then at some point, your code will be scheduled again, because during the time that you were doing this, you might have context switched to another process. So at some point, you get scheduled. When you get scheduled, you start from the faulty instruction again. And this time, when you access, now you have the page table translated to you. So you can just go and find it in memory. I really wanted to do this one. What time is it? 5 minutes. Yeah. Okay. So I'm gonna actually point you to the lecture I gave last term on this one. So I'm gonna jump over them and try to do other stuff. So in this slide, I show you how basically expensive demand paging is. So if you remember, effective access time is basically hit time plus miss ratio times miss time. Now, let's say you have memory access time of 200 nanoseconds. So this is how much it takes for you to go to memory. Let's say it's 200 nanoseconds. And then let's assume that in order for you to take care of a page fault, it takes 8 milliseconds to basically go to the physical memory, to the secondary storage and bring the data. Let's say that takes 8 milliseconds. And for now, let's assume that the miss ratio is P. So let's not make any assumption about P, and then we'll just change P and see how things would change. So if you use these in this formula, your effective access time is going to be your hit time, which is basically the time it takes for you to go to memory, which is basically average access time to memory, 200 nanoseconds, plus miss ratio, P, times the time that it takes to handle a page fault, which is 8 milliseconds. So if you put them all together, it would be 200 nanoseconds plus P times now 8 million nanoseconds. So just compare these two numbers. This is huge. So let's now look at P. Let's say P is 1 out of 1,000. So let's say every 1,000 instructions, you get a page fault. What is going to be your access time? It's going to be 8.2 microsecond. That's 40x slower than just accessing your memory. 40x. Now, in order for you to get only 10% a slowdown, you need to have a single page fault every 400,000 accesses. So this is 40 times worse. If you need 10% worse, then you need to have 1 page fault every 400,000 accesses. So that's the effect of this huge cost of taking care of page faults. Okay, what are the factors that are important that would lead to misses? It's similar story as we had with caches. You have compulsory misses. These are the misses that you incur if this is the first time you're accessing a page. The way to deal with it is basically prefetching. You can prefetch, but then prefetching is also, important for you to not prefetch a lot, because if you prefetch a lot and you don't end up using them, you're wasting memory. So it's kind of like a tricky thing to decide how much to prefetch, and whether or not to prefetch. The other one is capacity miss. As before, the way to solve it is to have bigger caches. So in this case, have bigger memory, larger memory. The other one is conflict misses. You don't have it here because your physical memory is, as we said, it's fully associative. So you don't have any conflict per se. Now, the other miss that you could incur in memory is policy misses, which is basically as a result of your bad replacement policy. Maybe there was no space in your memory, and then you decided to throw out a wrong page. If you throw out a hotspot page, a page that is accessed a lot, then you're going to miss in that page access, and that's the result of your bad policy. So I think I'm over, but because I started 5 minutes late, I'm going to go 5 minutes over, so that those of you who have to go, please log off, but then make sure to watch the last 5 minutes of the lecture later on when it's posted. Okay, so now let's look at the policies that you could think of when it comes to replacement. One is random, so randomly pick a page to evict. This is simple, but it leads to very unpredictable results because you're randomly picking. The other one is first come, first serve. Basically, whichever page that has been staying in the memory for a longer time, you just get rid of that one. But then it's kind of fair. You're giving the fair share of time to each one of the pages that you're bringing to memory, but it's not optimal. The performance is going to hurt, because what if the page that has stayed longer is indeed the page that is used more? So you probably want to keep it in the memory instead of throwing it away. The other one is minimum, which is kind of like optimal. It's not kind of optimal, it's actually the optimal one. You can prove that if you replace the page that won't be used for the longest time in future, then that's optimal policy. That's optimal replacement policy, meaning that it leads to optimal performance. Now you can prove that. However, very similar to all the other optimal policies that we have talked so far in the course, this is also impractical because it needs you to know what's going to come in future. How do you know if a particular page is going to be used for the longest time in the future? You don't know the future. But we're going to use it as a benchmark, as we did it before with other policies, with other optimal policies. So it's impractical because we don't have any idea about future. However, we can use it as a benchmark to see if we can get close to it. Now, the one that is used usually is called least recently used. So the idea is to find the page that hasn't been used for a longest time. So if you find a page that hasn't been used for the longest time, that gives you an indication that this page is probably not going to be used in the future. So it's basically you're using the history to predict future, right? So it's kind of like you're trying to approximate the mean policy. So this one is an approximation of this mean. How do you do this approximation? You're basically guessing, right? Based on the history, you want to predict about future. Now, this seems like LRU. Sorry, the LRU seems like mean, but it's not exactly mean, as there are examples to show the difference. And this also turns out to be pretty expensive to implement. So if you want to exactly implement least recently used, it has high overhead and high cost. So people usually approximate LRU. So what you get is an approximation of LRU and LRU is an approximation of mean. So you get 2 levels of approximation in modern systems. That's pretty much what you get. Okay, so I'm going to actually end the lecture here. Yeah, so on Tuesday, I'll walk through some of the important stuff that is left in this slide, and I start the I/O discussion. So yeah, thank you for those of you who attended the lecture. Sorry I went over time. I wanted to cover the time I was late at the beginning. And thank you for those of you who are watching online after the recording of this. So take care, be safe, and talk to you later. Bye-bye.